so the third type of intermolecular attraction that we talk about is called hydrogen bonding. So to make a hydrogen bond, you need two things. You need a hydrogen that has partial positive charge density, and you need an atom that has a lone pair of electrons. Okay, so under what circumstances will a hydrogen have a partial positive charge? Sorry, that should be partial positive. Under what circumstances will hydrogen and the molecule have a partial positive charge? Well, it will only have a partial positive charge if it's attached to something that's very electronegative, that's more electronegative than itself. So hydrogen's electronegativity is 2.2, so it needs to be attached to something that's more electronegative than itself, and difference in electronegativity needs to be greater than 0.35. Right, could be a polar covalent bond. So that means the atom attached to hydrogen must have an electronegativity greater than 2.55. Or, no, we said 0.4, right? Difference of 0.4. So that means the atom attached to hydrogen has to have electronegativity greater than 2.6. So pretty electronegative atoms. So where do you find pretty electronegative atoms at in the periodic table? In that area, because if you remember, fluorine is the most electronegative atom in the periodic table. So if hydrogen is going to be a partial positive, then it's going to be attached to something very electronegative, like fluorine, the most electronegative atom in the periodic table, or oxygen, or chlorine, or nitrogen. Those are the four most electronegative atoms in the periodic table. Right, so in which case so fluorine will be partial negative, oxygen partial negative, chlorine partial negative, nitrogen partial negative, and then hydrogens will be partial positive, right? Right, but HCl, not a very interesting molecule, and HF, not a very interesting molecule because you can't attach anything else, because fluorine only likes one bond and hydrogen only likes one bond. But if it's attached to oxygen, that can be an interesting molecule, because oxygen typically likes to make two bonds, so something else can be attached out here. And nitrogen likes to make three bonds. Oops. So something else can be attached here and something else can be attached here. So you can have molecules in the complex molecules in those cases. So molecules with OHs and molecules with NHs are all over biological chemistry, for example. Okay, so if we take an example of what is hydrogen bonding. So if we had two molecules of water, for example, so how would two molecules of water be attracted to each other? Well, so first thing that you need to do is assign partial charges. So hydrogen's partial positive, and oxygen is partial negative. So how would another molecule of water, so if two molecules of water approached each other, how would they align each other so that there's an attraction between them, between each other? So what it would do is it would approach each other like this, so that the hydrogens of one molecule would be near the oxygen of another molecule. And then there's an attraction between that H and this O, and between this H and that oxygen. And so this is an attraction. All right, so all these intermolecular forces that we're talking about, or intermolecular attractions, are electrostatic in nature. Positives are attracted to negatives. So in this case, it's a partial positive hydrogen attracted to a partial negative oxygen's lone pair. And so this type of attraction we call chemists call hydrogen bonding, right? Why? Why do we call it that? Because it involves a hydrogen atom, right? It involves a hydrogen atom that's attracted to another atom in another molecule. That's a hydrogen bond, and it's represented by dotted line. So if you're ever asked to sketch the hydrogen bonds between two molecules, line up the partial positive hydrogen in a molecule with a partial negative atom in another molecule, draw a dotted line between the hydrogen and the oxygen. So what is water molecule? So what does water look like? So if you just had a beaker of water and you were small enough to see all of the atoms at the atomic level, well, so each water molecule has two partial positive hydrogens. And so each of those hydrogens can be hydrogen bonded to another oxygen of another molecule. And each of the oxygen has two lone pairs. So each oxygen in every single molecule can be hydrogen bonded to two hydrogens. So every H2O can donate two H bonds and accept two H bonds. Right, so this would be accepting, right, hydrogen bonds from another molecule. So with respect to this water molecule that I have circled, right, that oxygen accepting two hydrogen bonds, and it's donating two hydrogen bonds to other water molecules. So at the molecular level, that's what water looks like. So if you want to make water boil, then you need enough energy to break all of the hydrogen bonds to a molecule. So you need enough energy to break 4 hydrogen bonds to one water molecule, and then that water molecule can escape into the gas phase. So to make water boil, of course, it's got 100 degrees Celsius boiling point, so pretty high boiling point to make water boil, to get molecules to start evaporating into the gas phase. Okay, so if we take another example, so if we take this molecule, right, can it make hydrogen bonds? Or so we've looked at 3 types of intermolecular attractions now: hydrogen bonds, dipole-dipole attractions, and van der Waals attractions. So which one, and the one that's the strongest is hydrogen bonds. And then dipole-dipole is second strongest, and van der Waals is the weakest. So can this molecule make any of those 3 intermolecular attractions? And if so, let's pick the one that's the strongest. So can it make a hydrogen bond? And so to make a hydrogen bond, it needs two things, right? It needs a lone pair of electrons. Got that? On oxygen. Needs a hydrogen that's partial positive. Does it have a partial positive hydrogen? And the answer is yes. Right, that one right there. And oxygen's partial negative. And of course, carbon is also partial positive. And the other hydrogens, right, these hydrogens are not partial positive. Again, technically they are slightly partial positive because carbon's a little more electronegative than hydrogen, but the difference in electronegativity between carbon and hydrogen is so small that we just ignore it. Because all of the CH bonds, again, are non-polar covalent, so we ignore the electronegativity difference between them. But the carbon, because of oxygen, is partial positive, and the oxygen is partial negative, right? Again, because oxygen's electronegativity is 3.44, carbon's is 2.55, and hydrogen's 2.20. So between oxygen and carbon, 3.44 and 2.55, we said it was 0.89. And between oxygen and hydrogen, 3.44 and 2.20, a difference of 1.24. So they're both polar covalent bonds. So it's appropriate to use partial positive, partial negatives to describe the electron density in the molecule. Okay, so anyway, back to hydrogen bonds. So how would these two molecules be attracted to each other? Then again, just draw another molecule and line up the partial positive hydrogen with the partial negative oxygen. And the CH3 is basically not doing anything, it's just tagging along for the ride. So we line up the partial positive hydrogen with the partial negative oxygen between the two molecules. And then we draw a dotted line between them. And we have illustrated the hydrogen bonds between the molecules. So again, if you want to make so this molecule is called methanol. If you want to make methanol bowl, then you have to give it enough energy to break those hydrogen bonds, and then it can escape into the gas phase. Okay, so if we took one more example. So let's take this molecule. So can it make hydrogen bonds to another molecule of itself? If yes, then sketch the hydrogen bonds. That's basically what you would have to be able to do on a test in this chapter. So in this chapter, there's lots of drawing. It's very conceptual, drawing dipole-dipole attractions, drawing hydrogen bonding attractions, drawing van der Waals attractions. Or you'd be asked to, given molecules, put them in order of boiling point, from low boiling to high boiling. Okay, so can this molecule make hydrogen bonds? Well, it needs two things, right? It needs an atom with a lone pair. Nitrogen has that. And it needs partial positive hydrogen. And so the hydrogens on nitrogen would both be partial positive because nitrogen is much more electronegative than hydrogen. And then nitrogen would be partial negative. And so is this carbon, would be partial positive because nitrogen is more electronegative than carbon. That's also a polar covalent bond. But the carbon doesn't really matter because we're looking at hydrogen bonds, so it's the hydrogens that matter. And the other hydrogens in the molecule, these hydrogens, are not significantly partial positive, right? So we just ignore them. They're not doing anything, they're just along for the ride. The important piece of this molecule, where all of the chemistry happens at, is right there with the NH2. Okay, so if we want to sketch the hydrogen bonds between two of these molecules, so we could use a line formula, right? 3 carbons attached to nitrogen. So that would be CH2, that would be a CH2, right? That would be a CH3. So if we wanted to sketch the hydrogen bonds, so this hydrogen's partial positive, that one's partial positive, nitrogen's partial negative. So let's just draw another molecule. And line up a partial positive hydrogen and a partial negative nitrogen with the opposite in another molecule. And then draw a dotted line between them. So that H is attracted to this nitrogen, and this H would be attracted to the lone pair on that nitrogen. So the other hydrogen, of course, could make a hydrogen bond as well. So if we have a nitrogen with 2 hydrogens attached and 3 carbon chain attached, carbon chain doesn't do anything, so it's really not that important in this case. And then if we sketch the hydrogen bond, that hydrogen will be attracted to the nitrogen as well. But you wouldn't have to show all of that. I would be happy, I would be fine if you just sketched that. Just show the in the molecule being attracted to another hydrogen, and the hydrogen in the molecule being attracted to the nitrogen of another molecule. And that would be sufficient to illustrate hydrogen bonding in the molecule. But at the molecular level, if you looked at the molecule, both H's would be hydrogen bonded to other nitrogens in other molecules. Okay.